Now we'll take a moment to distinguish between an exponential function and something called a logistic function. Not everything that starts out growing exponentially continues to do so forever. Right? A lot of things have, like, they can't grow to infinity. They might have, like a carrying capacity of some kind if the function is modeling population growth, or maybe something like a sickness, like people contracting diseases, right? That can't, infinitely many people just can't become ill. So logistic functions are a special type of modified exponential function that have this kind of like limiting value, or they start off exponential. So you can see here that these both kind of have the same sort of growth in the beginning, but instead of increasing off forever, where the growth is not restricted, they start to level off, and they actually have this sort of horizontal asymptote here. Okay, so let's just kind of compare and contrast the formulas and all the different properties that each of these things have. So it's really important to understand that this exponential function here, right, the growth is not restricted, versus with a logistic model, the growth is restricted, right? There's some kind of thing in the environment that's causing this unlimited growth to not be possible. Okay, so for exponential functions, the model, right, as we've seen, I'm just going to expand this a little more. And actually, instead of x, I'm going to use t, because we're going to use these to talk about things generally with time as the variable. And these can look like e to the t, or e to the some maybe number times t. And maybe there's even an initial value in the front multiplied. So write that as a times e to the kt. Just like PERT, except we're using different kind of letters here. Okay, so the a here, again, is the initial value, or the y-intercept. So on the graph, we can see that that's right here. All right, that height would be a, or the coordinate would be 0, a, if we want to be a little more specific. The k here, as we just talked about, it has an indicator of how fast the function's growing. So the k is really important to take note of if you want to see if the function's growing or decaying. Okay, so this is called the growth rate. And if k is positive, then this is growth. And if k is negative, then it's called the decay rate. So if this value here is positive or negative, that tells you if your function is growing or decaying, right? Decay would look like this, like that's not great, but the opposite kind of relationship, decreasing forever. Okay, logistic functions, they involve exponential functions, but they look different. Okay, so here is what the format algebraically, or function notation wise, what this looks like for a logistic function. So it's a fraction. Right? Things with horizontal asymptotes tend to be fractions. And there's a number up top, which I'll use C for. Then in the bottom, we do have an exponential part, but first there's maybe a number added. And then we have this, basically this part just over here. So this is C over A plus BE to the negative KT. Now I know a lot of letters here, but this t is the variable, right? Just like it is over in the exponential formula here. And the a, the b, the c, and the k are all numbers that would be present for your specific situation or for the specific formula. Okay, so a couple properties about this function, right? As I mentioned before, we have this horizontal asymptote here, or this limiting value, or if you want to think of it as a carrying capacity, that's okay. If your function here, right, models like population growth, right? More generally and mathematically, this is a horizontal asymptote. And what we would do to find this is we would let t go to infinity, and we'll work through this in a specific example, but the formula ends up being c over a. The limiting value is c over a, where this c comes from the numerator of the logistic function, and this a comes from this number down here that's added to the kind of exponential part. Another characteristic of this graph that's interesting is right here, right, where the function kind of switches its personality or it changes its behavior, right? It was kind of exponential at first, and then it stopped doing that. It started becoming something different, actually closer to maybe logarithmic. And so this mixed variant is called logistic. But this place here, and we'll come back to this when we learn more, review logarithmic functions, but this is an inflection point. Right, this is a point of inflection. This is where the concavity changes. Right here it's concave up, and then over here it's concave down, right? So the inflection point, why this is interesting in terms of a function that models some kind of real life situation, right, is that this is where the graph is the steepest, right? And we've talked about this before. This is where the tangent line, the slope is the steepest, right? It's still growing, but right around here, it doesn't grow as quickly. Okay, so this is where the growth is the fastest. We will learn a shortcut way to find these because taking the second derivative of something like this isn't too fun. But for now, just recognizing where that is on the graph is good. Okay, so here's an example of a logistic model. Like I said, these tend to model population or spread of disease. And here we have a bacterial culture that grows according to this logistic growth model, where we have Y is the weight in grams and T is the time in hours. So we've got 1.25 over 1 plus 0.25 E to the negative 0.4 T. Right, so we can see here that like this is really C, right? And then we've got A plus BE to the negative KT. So that's what I was trying to write in a more general format, but here we've got numbers for everything. Right, and again, this T here is our variable, and E, remember, is not a variable, it's a number. Okay, so part A says, what is the weight of the culture initially, then after 1 hour, and then after 10 hours? Okay, so here there's nothing fancy going on, right? We just want to actually find the value of Y when T is a certain number. So initially, right, this means T equals 0. So let's do Y of 0. So we're going to plug in a 0 for T. And when you do that, you get 1 gram. Actually, not approximately, it's just equal to 1 gram. So initially there was 1 gram of this bacteria culture there. Okay, after 1 hour, we'll do Y of 1. So that'll be 1.25 over 1 plus 0.25 E to the negative 0.4 times 1. Okay, and that comes out to be about 1.07 grams. So, it's growing. It's not growing a whole lot in only 1 hour. But here's a graph of this function here. We've only got it starting at T equals 0 because, of course, T is measuring time. Initially, we have 1 gram, and then after 1 hour, it's a little bit above 1.05. So right here, 1.07. Now after 10 hours, let's see what we've got in our culture then. So Y of 10 will be 1.25 over 1 plus 0.25 E to the negative 0.4 times 10. Okay, and that comes out to be about 1.24 grams. Okay, so we can see in our graph here, like here's 10 hours, and based on the graph here, it looks like we're kind of approaching that horizontal asymptote. Which brings us to part B. What is the limit of the model as T increases without bound? So as time increases forever, as time goes on, if you were to just leave this culture alone, what would be the maximum weight that it could take on? Right, so the bacteria culture isn't going to continue to increase and become infinitely heavy, right? So an plain old exponential model isn't going to be a good fit for that extended domain. So we're going to find out like what is it going to level off towards in its weight. So we're going to let T approach infinity. Okay, so we're going to take the limit as T goes to infinity of 1.25 over 1 plus 0.25 E to the negative 0.04 T. Now, I did tell you when we were introducing these kinds of functions that the horizontal asymptote is going to be given by c over a. So we should get 1.25 over 1 as our answer here, but I'd like to go through this so you can see why instead of memorizing the formula. So what I'm going to do here is just kind of plug in infinity. Now I know that that's not a number that you can just plug in, so I'm going to put that in quotes. But it can help us see, what's going on here. So I'm not going to write limit anymore because I'm just trying to evaluate it now. And instead of t, I'm going to replace that with infinity. Now, -4 times infinity does not follow the proper kind of rules that our numbers tend to follow. So this actually is just the same as -infinity. Okay, so I'm just going to simplify piece by piece, starting with the exponent. So we'll have e to the -infinity down here. Now, e to the -infinity is something that we talked about, right? This limit here actually approaches 0. Okay, so what we'll have here is 1.25 over 1 plus 0.25 multiplied by 0, right? 0.25 times 0 is just 0, so that's 1.25 over 1, or just 1.25 grams. And this will happen no matter what B was, no matter what K was. When you let this go to infinity up here, basically this whole part here just approaches 0. It becomes very, very tiny. And so that's why what we get for this limit will always be the numerator number over that first number, the a here, so c over a. Okay, and of course in our graph over here, we do see this. I mean, it's sketched in here as the horizontal asymptote of 1.25. Okay, part C says, when will the weight of the culture reach 1.5 grams? Now that would actually be setting this equation equal to 1.5 over here, and then trying to solve for t. We haven't in this class talked about logarithmic functions, but we will very soon. But that would be required for us to sort of solve for a variable that's up in an exponent like that. We actually don't need that here though, right? Because we know that the culture isn't going to really extend beyond 1.25 grams, based on this model at least, right? It's impossible that this culture will reach more than that. Okay, so in this case here, we could say that it never will, right? The limiting weight or the limiting size is less than 1.25 grams. Okay, so I hope that this gave you a decent review of what the natural exponential function is and what a logistic function is. Next time, we will talk about the derivative of the natural exponential function, get some rates of change involved, and have some fun with that.